The next chapter is about flattening. That tells us how to put the image then at the end into our neural network. Again, it will be a relatively short section, and we want to take a look at the idea first of all, before we add the code. So the CNN part is actually done. Of course, without the backpropagation, we will do that then after we're done with the flattening. But we still have images. So we still have 3D objects that we have to pass on to our dense layer, which expects a two-dimensional matrix where every row corresponds to a data point and every column to a feature. So we somehow have to turn our images into that format. And that's what we do here in the flattening layer. So that's essentially the link between all the convolution and the actual network. Both parts have learnables, of course. So the network, of course, has the weights in the neurons. And we learned already that the convolution kernel themselves are like neurons. So the weights are the weights like in the neurons. And we also have a bias for every convolution filter. So both parts are learnable, and just know we have to link these two parts. And that's called flattening. So there's a nice plot or a nice image from the Keras webpage just to illustrate this. So you have our matrix, and then you arrange the matrix in a particular way, and to get a vector. So you turn a matrix into a vector. How you do that, so what the order is, does not matter, as long as it's always the same way. And that's what we want to do now. So we want to link the CNN to our dense layer. And that's where we want to add the last class now, and that's the flattening class. And we want to add a forward part, and the forward part is just rather simple. So we take our matrix M, and then of course we have to determine the shape of the matrix as we did many times before. So again, X and Y are the image coordinates, then we have the number of channels, and at the end, the number of images, so everything in one matrix. We want to save the input M just to make sure that everything works correctly. And then we have to determine the size of the vector for every image. So what is the size, or what is the information first of all? So we have the image itself, which has the size or the number of data points or number of pixels, which is X times Y. But that's true for every channel. So we multiply this with the number of channel. And that's the number of data points or features that represent one single image. So L corresponds to one single image. And just picture now that every image is one data point and the number of features is L. And we have an L times number of image matrix that we feed into our dense network. And we also have to check this then. So that's our that's the length of the vector. So we now want to assign or pre-allocate the output matrix for that. So number of images times L. So every image is now a data point, and L is the number of features. And we want to make sure that we arrange this in a correct way. So we want to use, just for this course, a rather slow for loop. There's a clever way to do that. You probably know in TensorFlow, so that's and which is a lot faster. But here in this case, I really want to illustrate what the code actually does, and that's why I just want to have this rather slow for loop just to illustrate how it works. So you just take for every image all the information, and then you reshape it to a vector that has one row in L columns, which will be one row in the output matrix. Well, and that's already it. So that's our output. So, and we want to implement this now in our CNN or in our module, and then want to run it, of course, and test it. So that's a new chapter again. So we just close this, and then we just go to our work folder, and then we just add the next chapter, flattening. All right. We also don't need this here. And we also move to this folder again. So if you wish, that's a kind of primitive way for version control. All right, so then we saved it here, and we save it here as well. All right, so we now just add the last part, and there's no order in our module, but I always like to do this in the order you would actually have in the actual convolutional neural network. So you read the images, have convolution layer, max pool, layer dense, then you have all these different activation functions at one place. So just in the structure and the architecture of a convolution neural network, you would put it between the dense layer and the convolution layer, which in our case is after the max pool, so in front of the dense layer, so to say. That's where I want to put it. So we just add a new class, and we call it flat. All right, and then we define a forward method where the input is m. And we also want to save it, of course. And we also want to determine the shape of the matrix. So we can just copy and paste that as well. All right. So now here comes the actual flattening part. So we determine the length of the vector. And this vector is one image, or let's say it like this, is one image, means one data point. With L features or dimensions as you want. So it's just the number of channels times the number of pixels. So we just have this here. All right. And then we can therefore pre-allocate the output matrix. And the number is, so the size of the output matrix is the number of images times L. Every image is now a data point with L features. And now we just do this with a rather slow for loop. So we can just say for I in range. And then we have a number of images, of course. So we do this for every image. And then we just put it into our output. So all for image I, all rows, that's our image I, all columns. And then we just take M, all rows, all columns, all channels for this particular image. And that's it. So now we just need to save the output. All right, so then let's just test the code and see whether we get a matrix of the correct size. So we would add the flattening layer at the very end. So let me just call the module again. We still have all the variables saved from the max pool, so we don't need to rerun everything here. Now we just want to run the flattening or add the flattening layer. So we just call it flat, I would say. And then we just say flat is the flattening layer, and the autocomplete should recognize it. And then we just add the flattening layer. So then we just say flat forward, and M is the output from the last layer. So that could be a max pool layer, for example. Now let's see whether we get an error message. Ah, yeah. Of course, we have to have an output. All right. So here we go. Have to call it again. And now let's say, see whether we get an error message. We don't get an error message this time. And now let's take a look at the output. So that should be just a vector. And what is the size of the vector in our case? So we have 5 images. So it should be 5 times something. So let's take a look at this. So 5, that's good. And now let's see whether this 5,120 makes sense. So let's take a look at the output from the last layer. And let's take a look at the shape. So it's 32 times 32. That's the size of every image. And then we have 5 images, of course. That's this number here. But then we have 5 channels each. So this here should be 5,120. In fact, it's 5,120. So that's the number of features in an image. And we can also just take a look at this. So for example, we can just save this and a matrix, let's call it test. And then you have an idea about those values. And they're rather large, right? And we have only actually 2 convolution layers. Then we had 1 convolution layer max pool, and those values are pretty large already. Nevertheless, has the correct shape and the correct number of dimensions. And that's our flattening layer. And that's actually it. So we just checked it. And of course, please check whether the autocomplete recognizes this method and this class in the module. And now we have all the ingredients we need for our CNN. So we have the convolution layer, we have a pooling layer, we have activation functions, we have the higher optimizer, we have flattening, and we have the dense layer. And what we now need in order to enable it to learn is the backpropagation. And that will be the biggest part of the whole lecture, because now we have to add the backpropagation for the pooling layer for the flattening, that will be not a big deal. And also for the activation functions, that would be rather easy. However, we also, of course, have to add a backpropagation time for the convolution part. And that will be a bit tricky. But I guess if we just follow the math as a guideline, also the orientation of the matrices and the shape of the matrices as a guideline, it will help us not to get lost and to understand how to implement the backpropagation.